Hello guys, welcome on Tesla Adventures. In this video, we are going to discuss the concept illustration problems of type 3, which is based on the graphs, but of level 3, which is based on exclusively for JEE Advanced as well as Physics Olympiad stage 1. So first of all, let us see that there is a 1 mole of a monoatomic gas whose molar mass is m, and it goes through a cyclic process as shown in the figure. This cycle is being plotted between the density of the gas as well as the pressure of the gas. So we have to find out the heat rejected by the gas in one cycle and the efficiency of the cycle. So first of all, let us do one thing, that let us name the volume at point 1 as V0, and we know that this graph would be passing through origin, although it might seems by the figure that it is not passing through the origin. But if you check the slope, then if we assume that this graph is passing through the origin, then its slope would be rho naught by P naught, and further on the slope of this line is also rho naught by P naught, which means that this line is passing through the origin. So if this line is passing through the origin, so you can see that in this process 1 to 2, density doubles and therefore volume becomes half. So let us assume that volume of point 2 is V0 and volume of point 1 is 2 V0. And again when we are going from 2 to 3, this volume, the density is becoming half and volume will become double. So it would be 2 V0, and obviously 3 to 1 is a isochoric process. Now let us first of all calculate the relation between density and pressure. So we know that PV is equal to nRT, and as we know that N is equal to mass upon molecular mass and RT, and P will be equal to M by V RT by M. And as we know that molecular mass mass of the gas will be molecular mass because number of moles is 1. So we can write down it as rho naught, rho, and pressure will be equal to rho RT by M. Okay. So this is first of all the relation between P and rho, and you can see that in process 1 to 2, this is a isothermal process because pressure, in fact this is yes, it is a isothermal process because in process 1 to 2 you can see that pressure is directly proportional to, or density is directly proportional to the pressure, because P rho and P graph is a straight line graph. So density would be directly proportional to the pressure, and if we find out the temperature at this process, in this process, then it would be constant. So T will be constant, because if T will be constant, then only density will be proportional to the pressure. So this is a isothermal process, and in this process you can see that volume is decreasing. So temperature is constant, so du will be 0, and volume is decreasing, therefore work done will be negative, and Q will be negative. So let us suppose that the heat exchanged by the gas with the surrounding in this process 1 to 2 is Q1, and that would be equal to dW, and obviously dW is negative, so this is the rejected heat, because negative heat is the heat rejected, and dW will be nRT ln V final by V initial, and it would be 1 by 2, which can be written as minus of nRT ln 2. This negative sign denotes that Q is rejected heat. Now N is 1, so we can say that Q1 will be equal to W1, and it would be equal to minus of R T, and T is either of temperature of 1 or temperature of 2 because these are same, ln 2. Okay, now let us move on the next page. Now in the next page, let us again write down the volumes V naught, and this is 2 V naught, this is V naught, and this is again 2 V naught. So the work done and the heat extracted in the first process is this one, minus R T1 ln 2. Now what we can say, that at this point we do not know the temperature, so we have already created a relation that P is equal to rho RT by M. So P is equal to rho RT by M, and M is the molecular mass of the gas which is given in the question. Now what we will do, we will use the value of temperature at this point, or either we can use the value of temperature at this point, because it would be same, because this is an isothermal process. So at this point you can see that the pressure is P naught and density is rho naught R T1 by M, and therefore T1 will be equal to P naught M by rho naught R. So this is T1, and RT1 will be equal to P naught M by rho naught. So we can substitute the value of this in Q1. So Q1 will be, W1 will be minus of this is minus of R T1, which is P naught M by rho naught ln 2. This is heat rejected and work done on the gas or on the system. Now in process 2 to 3, let us write down it with different color. 2 to 3. 2 to 3 is a isobaric process, and in this process volume is increasing and pressure is constant, which means that the temperature will increase. V increases, T increases, and P remains constant, which means that dq will be positive, and therefore this would be the heat supplied to the gas, and it would be equal to NCP delta T. So dq, let's suppose it is Q2. Q2 will be plus, N is 1. It is a monoatomic gas, so for monoatomic gas Cp will be 5 by 2, because Cp is 1 plus F by 2, and F for monoatomic gas is 3, so it is 5 by 2 R, and delta T is T3 minus T2. Now T3 is obviously, or we can say R T3 will be equal to rho naught. In fact it would be equal to 2 P naught into M by rho naught, and R T2 will be equal to 4 P naught. In fact it would be 2 P naught upon into M by rho naught. Rho naught is also equal to 2 rho naught. So Q2 will be equal to 5 by 2, and R T3 will be 2 P naught M by rho naught, and R T2 will be P naught M by rho naught. So it would be equal to, Q2 will be equal to 5 by 2 P naught M by rho naught. This is positive, and work done will be equal to P delta V, and P is 2 P naught and delta V is V naught. Okay, this is delta V. So we have to find out the value of P naught V naught, obviously in terms of P naught and rho naught. So what we can do, we can work done will be equal to 2 P naught into V naught, and we can write down volume as mass upon density. And I have already discussed this fact that this mass is the molecular mass because number of moles is 1, and if V naught is the volume at this point, then density will be 2 rho naught, and therefore it would be 2 rho naught. So work done will be plus of P naught m by rho naught. Now let us find out the heat extracted in 3 to this process, 3 to 1. So now in 3 to 1, let us again use the different color. 3 to 1, you can see that 3 to 1 is a isochoric process because density is constant and therefore volume will be constant. So V will be constant. So in isochoric process, heat rejected by the gas Q3 will be, first of all you can see that volume is constant and pressure is decreasing, so temperature will be decreasing. T is decreasing because P is decreasing. So Q3 will be negative. So Q3 will be, delta U will be 0. So in fact dW will be 0, work done will be 0. So Q3 will be equal to delta U and Q3 will be equal to NCV delta T. So Q3 will be equal to NCV delta T and delta T would be T1 minus T3. So Q3 will be equal to N is 1, CV is 3 by 2 R and it would be T1 minus T3. We have already calculated the value of RT1, which is P naught m by rho naught. So Q3 will be equal to 3 by 2 R into R is already taken inside the bracket. So RT1 will be P naught m by rho naught and this is P naught m by rho naught and RT3 will be 2 P naught m by rho naught. 2 P naught m by rho naught. So Q3 will be equal to minus of 3 by 2 P naught m by rho naught. So the total heat rejected will be the sum of negative heats, and the negative heats are Q1 and this is Q1 and Q3. So this is Q1 and Q3. So heat rejected, this is mod, obviously because we are already saying that it is being rejected, so we do not need to put an additional negative sign. So Q1 was P naught m by rho naught ln2. This is P naught m by rho naught ln2 plus Q3 is 3 by 2 P naught m by rho naught. So taking out common P naught m by rho naught and in the bracket it would be ln2 plus 3 by 2. This is the value of heat rejected and the heat supplied is the only positive heat in the process, which was in this process 2 to 3. So it would be 5 by 2 P naught m by rho naught. 5 by 2 P naught m by rho naught. And now if we find out the efficiency of the cycle, then efficiency we know is work done upon heat supplied, and work done will be equal to W1 plus W2 because W3 is 0. Okay, so W1 was minus P naught m by rho naught ln2 minus P naught m by rho naught ln2 and W2 will be equal to P naught m by rho naught. Okay, and heat supplied is 5 by 2 P naught m by rho naught. So 5 by 2 P naught m by rho naught. So efficiency will be equal to 1 minus ln2, okay, and divided by 5 by 2. This would be the efficiency of this process. Now we move on the next question. In this question, you can see that this is a PV graph or PV cycle for 1 mole of an ideal gas which is carried through three processes. One of this process is isobaric, in fact isochoric. One of the process is isothermal, and one of the process is adiabatic. So obviously we can see that AB will be isochoric and BC will be isothermal and CA will be adiabatic. Okay, with this we have already discussed in the previous videos, and this can be predicted by the slope. So we know that more steeper graph, which is a hyperbola, is adiabatic graph. Now first of all, let us find out this volume. So we can use from C to B, this is a isothermal process. So for a isothermal process, we know that PCVC will be equal to PBVB. PC is 3P naught, VC is unknown, PB is P naught, and VB is V naught. So VC will be equal to V naught by 3. So this is the value of VC. Now for C to A, let us apply PCVC to the power gamma is equal to PA VA to the power gamma. So PC is 3P naught, VC is V naught by 3 to the power gamma, and PA is P naught by 2, and VA is V naught to the power gamma. So you can see that it is 3 to the power 1 minus gamma, P naught V naught to the power gamma, and that is equal to P naught V naught to the power gamma divided by 2. So cancelling this, so you can see that 3 to the power gamma minus 1 is equal to 2, and ln 3 into gamma minus 1 is equal to ln 2. So gamma is equal to ln 2 by ln 3 and plus 1. Okay, ln 2 by ln 3 plus 1. And for ease of calculation, gamma can be written as ln 2, this is ln 2 by ln 3 plus 1 can be written as ln 3 by ln 3. So gamma can be written as ln 6 by ln 3. So this is the value of gamma. Now we move on the next question. In this question, you can see that this is a cyclic process and an ideal gas is going through the process 1, 2, 3, 1. And the efficiency of this cycle was 25%. And when the same gas is going through 3, 4, 1, 3, then the efficiency was 10%. So we have to find out the efficiency of the gas for the cycle 1, 2, 3, 4, 1. So first of all, let us see that in process 1 to 2, pressure is increasing and volume is increasing, and therefore temperature will be increasing, and therefore heat supplied will be positive. And in process 2 to 3, pressure is constant, volume is increasing, and therefore temperature will be increasing, and work done and delta U will be positive. Therefore heat supplied in this will be also positive. So let us write it down as Q12 and Q23. But in process 3 to 1, you can see that heat would be rejected by the gas because pressure and volume both are decreasing and Q will be negative. So efficiency is 25%. So let us write it in irrational form. So it would be 1 by 4, and that would be equal to the work done, which is the area of this graph, this bounded curve W1 upon heat supplied. So heat supplied will only be Q12 plus Q23. And now let us assume that Q12 plus Q23 is equal to A. So work done W1 is equal to A by 4. Now when we write down the efficiency of the second cycle, so you can see that this is 1341, and in 1341 you can see that in process 1 to 3 the heat is being supplied, because now we are going from 1 to 3, and while going from 1 to 3 pressure and volume both are increasing, and therefore du and dw both will be positive, and heat supplied by the gas, in fact heat supplied to the gas, will be positive. But in process 3 to 4 Q will be negative, and in process 4 to 1 Q will be negative, because in 3 to 4 pressure and volume both are decreasing, and in 4 to 1 pressure is constant but volume is decreasing. So what we can say, that the efficiency in the second cycle is 1 by 10, and that would be equal to the work done, which is W2, which is the area of second curve, divided by heat supplied is Q13. Okay, now this is W2, and W2 will be equal to Q13 by 10. Now we know that Q12 plus Q23 plus Q31 in this cyclic process is equal to the work done in this cycle, because you know that in cyclic process net heat is equal to work done. So Q31 will be equal to W1 minus Q12 plus Q23, and therefore Q13 will be equal to Q12 plus Q23 minus W1. So Q13 will be equal to A minus W1. So W2 will be equal to A minus W1 upon 10. Okay, so this is the work done in 2. Now in the complete cycle, this cycle 1, 2, 3, 4, 1, the efficiency will be the total work done will be W1 plus W2 upon heat supplied will be only, obviously in this process heat is being supplied only from 1 to 2 and 2 to 3. So it would be Q12 and Q23, which is A. So W1 can be written as, W1 was A by 4, and W2 is equal to A minus W1, which is A by 4 divided by 10. Okay, so this is the total efficiency, and this 10 would be in this side, yes, and divided by A. So this would be A by 4 plus 3A by 40 divided by A, and you can see that it would be 13 by 40, and in percentage neta will be equal to 13 into 5 by 2, which is 32.5%. So this will be the correct answer. Now we move on the next question. In this question you can see that these are three graphs. This is adiabatic graph, this one, and 2 and 3 are isothermal graphs. These three graphs are plotted in different processes for a same sample of gas which is having n number of moles, and that is ideal monatomic gas. So we have to find out the work done in process 2, which is another isotherm, and we have to find out the ratio of work done in 2 and work done in 3 from taking the from doubling the volume of the gas from V2 to V. So what we are doing, that we are going first of all from this point to this point from process 2, and we have to find out the work done, and we have to find out that ratio with the work done in process 3 in doubling the volume. So first of all, let us name that the temperature at this point is TA and temperature at this point is TB. Now we know that for monoatomic gas, gamma is 5 by 3, and we know that T1 V1 to the power gamma minus 1 will be equal to T2 V2 power gamma minus 1. This is the characteristic equation of adiabatic process in terms of temperature and volume. So at point A, we can say that TA, VA is V and gamma minus 1 is 2 by 3. And at point B, TB and V is 2V to the power 2 by 3. So TA V to the power 2 by 3 is equal to TB into 2 to the power 2 by 3 into V to the power 2 by 3. Cancelling out this one. So TA by TB will be equal to 2 to the power 2 by 3. Now we know that work done W1 in this process 2, let's suppose it is W2, is an isothermal process, and work done will be nRTA into ln2, and work done in W3 will be nRTB into ln2, and the ratio of work done W2 by W3 will be equal to TA by TB, and TA by TB will be 2 to the power 2 by 3. So this will be the correct answer. Now we move on the next question. In this question, you can see that there is a gas that undergoes a cyclic process A, B, C, again A. And the PV diagram of this cyclic process is shown. Now AB process is given as isothermal process and BC process is given as adiabatic process. While CA is a straight line on PV graph as shown, and it is given that work done in A to B is 5 joule. Work done in B to C is 4 joule. So first of all, from A to B, we know that it is isothermal process. So work done is positive, obviously. So it is plus 5 joule. And in process, isothermal process, heat is equal to work done. So it is plus 5 joule, which means that heat is positive and hence it is supplied to the system. In process B to C, it is adiabatic process, so delta Q will be 0. So heat is not supplied in this process, and the work done in this process is 4 joule. Okay, but this is the work done now. And the third thing is the fact that in the complete cyclic process, the work done is 3 joule because area enclosed is 3 joule. So net work done is 3 joule. Now we know that the net work done will be equal to the sum of work done in W1 plus W2 plus W3. So we can say that 3 will be equal to W1 is 5, W2 is 4 and WCA. So WCA will be equal to minus 6 joules, which means that you can see that volume is decreasing, so work done will be negative, and pressure is increasing and volume is decreasing. So we cannot say exactly that the temperature will be constant, but we have to predict this fact. Now we have to find out that the temperature is either increasing or decreasing, and that we can find out by the calculation of delta U. We know that in the first process delta U is 0 because it is an isothermal process. In the second process, delta U will be equal to minus of work done, which is 4 joule because it is an adiabatic process. And in the third process, delta U is U3. So we know that delta U1 plus delta U2 plus delta U3 will be equal to 0, and delta U1 is 0 itself, this is 0. So delta U3 will be equal to minus of delta U2. So delta U3, which is process C2A will be equal to minus of minus 4. So it would be plus 4 joules, delta UCA. And work done in C2A is this one. So we know that work done or heat supplied in C2A will be delta U in C2A plus work done in C2A. So heat supplied in C2A will be minus 6 plus 4. So it would be minus 6 plus 4 joule. And this would be equal to minus 2 joule. Okay, which is negative, hence it is extracted by the gas, and the efficiency will be net work done upon heat supplied, and heat is positive only in the first case. So net work done is 3 and efficiency will be net work done upon Q supplied. So net work done is 3 and the supplied heat is just 5 joules. So it would 3 by 5 and therefore efficiency in percentage will be 60%. Now we move on the next question. In this question you can see that n moles of an ideal gas, which is not given in the question, that whether it is monatomic, diatomic or polyatomic, and this gas is taken through this 4-step cycle 1, 2, 3, 4, 1. Now we have to find out the work done by the gas in this cycle in terms of T1, T2, T3 and T4. So we know that PV is equal to nRT, and when V is constant, then PT graph is a straight line graph. Therefore we can say that in process 1 to 2 the work done will be 0 because volume is constant. So, and in process 3 to 4 the work done will be 0. Now in process 2 to 3 the work done will be P delta V, and P let us suppose that it is PB. So it is PB, delta V is V3 minus V2, and this would be PB V3 minus PB V2. So work done in 2 to 3 will be equal to PB V3, which is N R T3, and PB V2 will be N R T2. So work done in 2 to 3 is N R T3 minus T2, and similarly work done in 4 to 1 will be negative because volume is decreasing. So what we have to do is the fact that we just need to find out P delta V mod with a negative sign. So P is, let's suppose, PA, so it would be PA into delta V will be let us use this positive sign. Let us find out the work done by V final minus V initial. So it would be T1 minus T4, and work done in 4 to 1 will be equal to in fact this would be V1 minus V4. Okay, so PAV1 will be NRT1 and PAV4 will be NRT4. So the net work done in the process will be NR is common, and T1 minus T4 plus T3 minus T2. It would be T1 minus T4 plus T3 minus T2. This would be the net work done in the cycle. Now we move on the next question.